Earlier today, Tom Marshburn spent a good bit of time assisting with a ground commanded activity. Saw a couple of small satellites flying inside the station to construct a 3D model of another object. The SPHERES experiment is familiar to those who've been following the International Space Station program. It got started on the space station during Expedition 8. But today's activity is part of the SPHERES-VERTIGO experiment. In this case, VERTIGO stands for Visual Estimation and Relative Tracking for Inspection of Generic Objects. And to learn more about this project, I'm joined now by Brent Tweddle. He's a PhD candidate at the Space Systems Laboratory at MIT in Cambridge, Massachusetts. He's a member of the SPHERES-VERTIGO team that ran this morning's test run and is, in fact, the man who was on the radio talking to Tom Marshburn during the activity. Brent, good morning. Was this your first time talking to astronauts in space?
Good morning. Yeah, actually, this was. It was an early morning for us, but it was really great to talk to Tom and see him work with our hardware for the first time on orbit.
Tell me how you got involved in the VERTIGO project.
So I've actually been involved for a good number of years. It started back in when I first came into grad school. My advisor, Professor David Miller, sort of said to me, look, we've got these SPHERES satellites that are on the International Space Station, and we want to put cameras on them and go. So it was sort of a blank slate that I had to go through, and we had a little bit of funding. We were partnered with the Naval Research Lab in Washington, D.C., and we built up a good ground prototype of this and tested it out with a couple of visual navigation algorithms. Then after that program actually was quite successful, we got some follow-on funding from the folks at DARPA to take the hardware that we built and transition it to an operational system that could actually be launched to the International Space Station. So that was a big part of my PhD, and we formed a team with a whole bunch of other sort of organizations, Aurora Flight Sciences in Cambridge, Massachusetts, and then we were integrated by STP and NASA Ames into the NASA process. And there were a lot of grad students and undergrads that joined the team, and we sort of put everything together, shipped our hardware, I think it was last August of last year in 2012, and it launched in October, and today was our first operations that went very well.
I want to get you to tell me about how so. Explain for those who are familiar with seeing these SPHERES satellites commanded to fly in formation on board the station. How does the VERTIGO experiment differ from what we've seen before?
Right, so SPHERES is a system, as you said, for formation flying, but it relies solely on a set of ultrasonic beacons that are installed inside the International Space Station to figure out where it is within the crew volume. And one of the things that we're looking at doing and sort of opening a whole bunch of research possibilities is to add a pair of stereo cameras, much sort of like the human eye set of stereo, or the stereo set of human eyes, to actually be able to see, perceive, and understand its world visually. And we use that information and communicate that information to the SPHERES satellites using a package that's called the VERTIGO goggles. And these goggles are they're sort of a 1.6 kilogram. They're almost like a netbook computer in terms of they have processing power, cameras, Wi-Fi device, a battery on board, and they're their own sort of little intelligence block that sticks on the front end of the SPHERES satellites and allows it to see the rest of the world that it wants to navigate through. You
provided us some pictures of that equipment that was used today, including the hardware that you've just described. It for all the world looks like you put eyes on the front of this sphere. Is that right?
Yeah, and it's sort of funny the way that kind of fell out. I mean, we weren't trying to make it look like anything, but a lot of people have commented it kind of looks like a Wall-E figure, but it really just fell out of the requirements of being able to see, build a three-dimensional map, having some processing power that we had, and putting some batteries and cameras on there, and we sort of followed the high-level system requirements, propagated it down to a design, and actually, in all reality, not all that surprisingly enough, it looks like sort of a human face when it is flying around the ISS.
Maybe the reason that our eyes look that way, because it works?
Yep, I mean, if it works, go with it.
And the trick, of course, is how you make this work. Can you give us a high-level explanation of how those goggles take in information that would help construct this model?
Yeah, so that's an interesting question. What we do is we run through basically an inspection algorithm where for this particular case, we're looking at an unknown object that we don't really know much about, but we want to build a three-dimensional model that we can use for relative navigation. So we fly around the other object, taking photos in sort of a trajectory, and then we match up what's known as feature points on each of the object. They sort of look like corners or sharp edges or things that are very distinguishable that we can match from frame to frame and from time step to time step. We put that all through various types of optimization engines, and we can come out with a geometric location for each of those features and start to build up a dense model, a lot like you would have a CAM-CAD model of the system from the visual information that is reprojected through the stereo cameras. That makes some sort of sense.
It does. And then is the data stored in the sphere itself, or transmitted to some other computer that's processing it, putting it together?
All of the processing for this is done on board the Vertigo goggles, and that actually led to a fair amount of effort in the engineering design. Is that we had to put a much faster computer on inside the goggles than the SPHERES satellites have had for years. So that computer is actually it's kind of a standard 1.2 gigahertz Linux computer that's embedded and customized in a couple of different ways, but we store it all locally, and we do the navigation with respect to that map all on board the actual satellite and all autonomously.
The next step then would be presumably getting that data to some piece of hardware that can crunch it.
Yes, we are. So once you actually have the model on there, then the algorithms are such that the goggles can actually crunch on that model and use that for navigation and high fidelity positioning and pointing if it wants to go and rendezvous or dock or then interact with the system.
So it's a very short turnaround. It's almost a real time. Take a look and make a map.
Yep, and that's exactly the idea. We, from a high-level perspective, you don't want to have the robot that is doing interacting with an unknown object in space, having to radio all of its information down to the ground and then radio it back up. The advantage of having a fully autonomous closed-loop system is that it thinks for itself on the fly, and even when there's very large time delays. And that obviously has appealing characteristics, but it also makes the problems very hard, and that's what the challenge is with this research.
Why is this worthwhile? Why would it be valuable to have a free-flying satellite be able to make such a map?
There's a lot of different and very good cases for looking at other objects in space. One of the ones that DARPA is interested is in going in and recycling old aperture satellites, which are some of the most expensive parts to launch, and refurbishing them for new spacecraft. And this is part of part of the DARPA Phoenix program, where they're trying to build up a new satellite by only launching the smallest elements, which is a really cool idea of basically space recycling, as best as I understand it. There are a couple of other applications, things like going to asteroids, which is sort of one of the NASA plans, and sort of understanding how that asteroid looks as you navigate around it and how it works even as it's tumbling and spinning, which is one of the additional challenges that you have in a space environment.
We're showing the NASA TV audience some video from the test this morning and seeing one sphere flashing lights at another one. How did the test go this morning?
So the hardware and the operational software part of it went great. It all worked the way the system worked when we sort of handed it over. Everything checked out fine, and so we have good good certainty that the hardware is working on orbit. The algorithms that were meant to do the circumnavigation and inspection worked pretty well, and we could see that they were going along the way they should. But they do need a fair bit more tuning and refinement. But that's exactly why we do these types of programs with the International Space Station, because we will be getting the data down as soon as tomorrow, be able to rehash and refurbish our algorithms, and we're hoping to operate actually on March 12th with a more refined version of those algorithms and get some of those milestones checked off.
So that's the next step, is another run just in a couple of weeks.
Yeah, it's a very short turnaround time, and that's really one of the benefits of operating with the crew on board the International Space Station.
And Dr. Marshburn was helpful?
Oh yeah, he was great. I mean, I can't say enough good things about how he operated in this test session. He was very, very professional, very thorough. I mean, all the results. It surprised me how well he did with this hardware that has never been turned on or operated even before. One of the tricky things is that we actually had to do a recalibration of the cameras to get high quality data, and it was a procedure that we were sort of holding our breath, that we weren't sure how easy it would be for the crew to do, but he just nailed it and got it right on, and we should be able to get good results now that we have that calibration very good.
Well, Brent will be looking forward to seeing another run in a couple of weeks and find out how well it's improved, how well we've learned from the first time.
Yeah, no, we're all definitely very excited, and there's still plenty of work for us to do.
Great. Brent, thank you for helping us learn a little more about this morning. Brent Tweddle is with the Space Systems Laboratory at the Massachusetts Institute of Technology and a member of the SPHERES-VERTIGO team.
Well, great. Thanks for having me.